Okay, so for all the people that joined later, my name is Milos and I come from Belgrade, Serbia, and I will be speaking about the geospatial analytics at scale. I come from a company called ThinkSolver, which is advanced analytics company located in Serbia. We are operating with clients mostly in the Balkan region, in some parts of Europe, and trying actually to push our job abroad. And in general, we are working in the following industries. So we have projects in telecommunication, in banking and retail. And you had a chance to hear from my colleague Valentina about the anomaly detection in telecommunication. And you can see some of our clients here. So we're working with the telecoms, like telco operators, members of the Telecom Austria group, some other financial institutions and retailers. And hopefully you will enjoy the talk today about the geospatial analytics. So is there anyone here in the audience that has some experience with mining geospatial data? Have you ever worked with geographical data in your project? Yeah, cool. Okay, there are some of us. So why is the geospatial analytics important? Let's first demystify this thing. Well, spatial context can be a very important information for various applications when we are working on some data project. It can be a really important predictive variable in many applications that we are building, because just by using spatial context we can really learn more and make better informed decisions. And of course we all know that massive volumes of geospatial data are generated on a daily basis, so we have various sensors generating data from various, let's say, industries or various production systems, etc. We have then GPS systems that generate also a vast amount of data. For example, if you take some taxi company or something like that, like let's say transportation company, a lot of this GPS data is generated on a daily basis. Of course, there is like weather data. We can use geographical data in, for example, if we have some IP addresses, so we want to, let's say, ban users for some part of the country. We know, for example, that from this region we have a lot of spam users, so we can do these sorts of things. Of course, search data also generates a lot of geographical information. Whenever we are using some search engine, so we are typing some query into our search browser, we are generating also some geographical data, because all these search companies, of course, use this information when they are returning the results based on for some search query. They are using this spatial context to return the most relevant results. Of course, social media, like, I don't know, platforms like Facebook, Twitter, etc., all of these platforms are using this geographical data. And spatial context actually can be a very important insight into behavior and mobility, so you can both track how certain customers, let's say, or certain things behave in certain areas of the world, or how certain things are mobile, so how certain customers, let's say, commuting from one place to another during the day or something similar. And all of this is used as information, of course, for us to make better informed decisions. In which industries do we have applied, let's say, geospatial analytics? Well, industries are basically seamless, so we can name probably, spend like 2 hours here just naming the industry that can benefit from geospatial analytics. But of course, one of them, of course, let's say by industry, we have various telco providers using this geo information, travel services, search engines, various applications or advertising. Let's say from my perspective, since we are working a lot with the telecommunication companies, they are of course using this geographical data to see, for example, if there are some outages or some anomalies in certain part of the country, so they can put their technical teams here to solve problems if they identify that there are, let's say, problems that are specific to this certain area of the country. Of course, various other organizations are using also this information, like public safety organizations, so in terms of law enforcement, civil security, public safety. Then in terms of disaster management, so for tackling, let's say, urban disaster risk, to various crisis responses, etc. For example, on Facebook, if hopefully you will never have a chance to be a part of this, but if you're in some region and there is like an earthquake, Facebook will prompt you to basically answer whether you're okay or something like that, and they're using this information to crowdsource everything about the, let's say, these crises that occur throughout the world. In climate change adoption, for example, also in social sciences, geospatial context is quite relevant, because all the researchers are putting a lot of effort to model the human and environmental interaction for certain regions of the world, etc. And I just put here a few logos for the companies that have a lot of geospatial data, and probably all of these companies are heavily using geospatial information. For example, for driving companies like Uber or Yandex, so they're using, of course, the geographical information to calculate the best possible route for your ride, so basically they don't lose money by, let's say, transporting customers from one place to another. TripAdvisor, of course, to recommend you the best, let's say, coffee shops, restaurants in the neighborhood. Facebook for various purposes. Probably you're not aware for everything they're using in geospatial information, and various other, let's say, companies and industries. And what questions do we try to answer with the geospatial analytics? Well, we can start with simple questions. For example, show me all the museums in this neighborhood. Since this is the first time I'm in Moscow, last night, for example, we wanted to go out and grab a dinner. So I went to Google Maps, I don't know, and just typed restaurants near me. And the browser that I'm using, they're using my geographical information. They know where I am currently at, and they're basically displaying me only the restaurants that are near me that maybe satisfy some certain criteria that I entered or something like that. But that's like the simplest question we can answer with the geospatial analytics. We can then go to something, let's say, more difficult, like how many people pass by this billboard per day. So let's say we're an advertising agency, and we want to know whether we should place our billboards, let's say, facing north or facing south, so we can actually track how many people pass by certain streets, let's say, which direction, so we can place the billboard in such a way that everybody sees it when they are commuting. Of course, what are the commute trends on a daily basis, so we can maybe plan some optimization for the traffic jams or something like that. That's like a big issue for my hometown. I think that's a similar thing you have in Moscow. I mean, during the rush hours, it's basically impossible to get from one place to the city to another. And this is how geospatial information can be used for let's say, to address this issue. For our telco clients, for example, in which areas my mobile subscribers have the network problems. So if we identify that for a certain region, we have a lot of outages, drops in terms of KPIs, low throughputs, whatever, we can be sure that we can be positive that there are certain problems in this part of the network, how much time we will need to get to location A, etc. And here as an example, you can see the query that I wrote. This is New Belgrade. In Belgrade, this is the part of the city where I live. So I believe the search keywords here were just data science. So since Google was using my geographical information, they returned Data Science Serbia, which is the local community in Belgrade, and Data Science Conference, which is the conference that happens in Belgrade. So just by using my geolocation, they managed to find the relevant results in the context where I was searching for, let's say, data science meetup, which I want to attend or something like that. And if I type the same query here in Moscow, probably, I mean, definitely the results will be totally different. Okay, but what are the challenges? Okay, it's all good about, we all know why it can be relevant to use geographical information, but why is it so tricky? Well, first of all, when we are dealing with the geospatial information, we are usually dealing with the really complex data types and really complex geoformats. In terms of, let's say, some of the data types we are using, of course, we have certain points. So location where I'm currently standing, so I basically just have X and Y axis and some values where I'm currently residing. But if we go into more complex, let's say, objects like polygons, multi-polygons, etc., these types and formats that we're using are quite complex. So in order to represent, let's say, a polygon, we need to have like a collection of all the points that describe this polygon. So, and our polygons might have holes inside or can be consisting of multiple polygons. So the situation here gets really tricky. And in terms of the complex geoformats, there are no, let's say, standards how to present the geospatial data. Of course, there are a few standards that we're trying to describe, but across the organizations, we're using different formats. For example, we have S3 shapefile, like the most common format, most utilized, which actually has a really good mapping for the geographical, let's say, region, and for the metadata that this region describes. But on the other side, we have some different formats like, I don't know, well-known text formats or XMLs or very different formats that describe geographical data. And they're really have problems to describe the meta information. So I can describe a certain polygon, but when I try to add the context of this polygon, what does it really represent, that's where the situation gets a little tricky. So you have various formats used across different organizations, and mapping all them together on the same scale can be really complex. Also, in terms of the operations that we want to perform on top of geographical data, that's also complex because, like, let's say calculating a simple thing, whether, I don't know, I am inside this building, so let's say I have a polygon that describes this building that we are currently in, and I have a point describing my location. So just performing this operation to figure out whether I am inside a building or out is quite complex in terms of computation, the resources that are required to calculate this information. Of course, various coordinate systems, various organizations use various coordinate systems. For example, most of us are aware of the standard that is actually called WSG84, I think, which describes our location as latitude and longitude. That's like the most common coordinate system. But different organizations use different coordinate systems, like we have the UTM. Various army military services use their own systems because they can be really hard to, let's say, be hacked by other organizations. So many of these army organizations have their own internal systems. NASA uses its own coordinate system. So we have a mess also in terms of presenting just a simple thing as latitude and longitude of a certain location. Of course, in terms of accuracy, it depends on how we are measuring this information of the current location. But if you use GPS, you definitely see that in many cases it's not working perfectly. It makes a lot of mistakes in terms of identifying the location of a simple object, which shouldn't be really that complex. And of course, vast amount of data, if we are generating for every event, let's say for our sales, for each visit to our web shop, etc., we can see that we are generating really a lot of data load. And which spatial data types do we use to describe the geographical information? Well, we have like simple things like point that describes a certain location, a location where some event happened, like that. So let's say latitude and longitude. But we can go with more complex data types like lines. Okay, lines are just a collection of different points that describe a certain line. So we are using them to, let's say, represent certain paths, trajectories, roads. And then we can go into some more complex things like polygons. So we want to describe a certain polygon, like a city, region, area, which is quite complex. And especially in some other industries, this polygon can be consisting, it can have some holes inside. It can contain of multiple unconnected polygons. One of such a things is in the telecommunication. So when you have like a base station that is projecting the signal that we are using on our cell phones, it's not spread and connected everywhere. So we have buildings, for example, where we do not have the signals, and the signal can be really covering a really large area, and all these polygons are not connected. So this is where the situation gets really tricky. Okay, and I mentioned the various data formats that we're using. So first of all, we have like something called S3 shapefile. That's the very common format, and from my perspective, it's the best way to present some geographical information. But don't take that for granted. For some things, it can be complicated. Why is the S3 shapefile popular? Because it has the ways to describe the metadata. So if I assign a certain location, let's say I'm standing right here, I can add metadata as, for example, why am I here, which conference I'm attending, what happened at this certain point, at what time. So I can really add the complex, let's say, context to this single geographical information. But it's really hard to parse, because if you take one shapefile, you will have all these files, like file.shp, shx, dbf. So you have like 10 files describing the single information. And that is why it's really hard to parse. And if you try to, let's say, use the code from Java to rewrite into another language, it's really impossible. It's really hard to do. It's not impossible, but these algorithms are really complex how to parse this file. On the other side, we have less complicated, let's say, formats like GeoJSON, which is humanly readable and easy to parse, because you can take single GeoJSON and figure out what is the information residing inside. but it's not that common and it's very verbose, so there are no like standards describing how this GeoJSON should be formatted always. And there's like OSM XML, which is also, let's say, humanly readable, if XML is humanly readable format. And it has clear structure, but when decompressed, it can be really huge. So you have a lot of lines in some text describing the simple, let's say, simple information or something like that. And there's like WKT, well-known text format, which is supported by various search engines, but it's not that commonly used in practice. And the list probably goes on. There are like probably 50 more different formats that we can use to represent our spatial information. And now, if we are talking about the operations performed on top of this data, so we managed to figure out what is the common format that we should use for representing our spatial data. Now we want to do some operations. So we want to do a simple thing like contains. So we want to figure out whether this certain dot here belongs to this polygon or no. That's like the simplest thing we can do. Or whether this is within this certain polygon. Also, we can do some kind of intersections, so we can see whether two polygons are intersecting, and as a result of this operation, we are getting a new polygon. So we have, let's say, the coverage of two different cells that are projecting Wi-Fi signal to some location, and the intersection of these two areas is where both these stations are projecting their signal. So as the output, we get a new polygon describing some new information. Of course, we want to perform spatial joins, so we want to join multiple polygons together. For example, we have the various municipality areas represented by some shape file or something like that. So you want to join them all together to see the complete city, how does it look like. And we want to index this data so we can use it much faster when performing these queries. So these operations combined with complex data structures and formats we are using add a new level of complexity in terms of working with geospatial data. Coordinate systems, the third thing. So in general, cartographic projection systems usually do not contain GPS coordinates because they're using some techniques to be more precise. And converting from one system to another is not that trivial at all. So for example, if we have coordinates written in one format, we want to rewrite it into another, transforming this information is usually quite complex. And here I just put as an example this Lambert conformal conic projection that tries to simplify the things for presenting a coordinate system. How does it work? So let's say this is the Earth, and what this projection tries to do is basically put it inside of a cone and make projection of this cone on top of the, let's say, Earth. And then once we roll out this paper, we're getting something like this. But what is the problem here? These two, let's say, points are really close. So we are losing some information by presenting this. And if we take a look on each, let's say, map of the world, we know that information is shrinked. It's not representing the world in the precise way as it looks like, so we see that, for example, I don't know, Greenland is too huge compared to some country or something like that. Of course, in army, for example, here are some standards used in, I don't know which armies across the world, but they have their own way to write coordinates. For example, in one of the cases where we are working on, we have the data coming in this UTM format, and then we are transferring it to WGS84, and I will talk more later about converting this on a scale, let's say. So what we can do with the open source tools and technologies, and what are the challenges to process this vast amount of data? Of course, I will be speaking here today only about the open source technologies, so I will not go into proprietary technologies that require purchasing licenses or similar. First of all, we want to parse vast amount of data, spatial data at scale. And there are some solutions that really perform well when doing with some geospatial analytics, but are not working at scale. One of them is Shapely. That's the application that works on top of Java, implemented on top of Java, that knows how to work with the geospatial data, but it is a single process. It cannot run in parallel on multiple machines. So if we're working about the processing large amount of data at scale, we cannot use Shapely because it is a single process and it always runs on a single machine as a single process. Let's say we want to perform some spatial joins, so we want to join multiple data sets together, multiple geospatial data sets together. S3 is scalable solution, so we can answer the first issue, but it doesn't perform with spatial joins. It cannot work, it cannot join two spatial contexts in one. We have GeoSpark, which has really complex APIs, so if we want to write some application, we really need to dig deeper into formality of how certain things are converted from one system into another, why a certain country decided to represent, let's say, this information in such a way. So we're not dealing with the things that we should deal with. We are going into completely different areas of exploration, research, work, so we are wasting a lot of time. Of course, you want to read various formats to work efficiently with geodata and to enable exploration. What this means, we want to, let's say, bring our data scientists and let them to do the exploration on top of this geospatial data, so they can easily write the queries and easily learn from this data, so they don't have to deal with all this hard programming and figuring out why certain function in C++ for converting from one coordinate system into another is implemented in this way and so on. So the next part of my talk will be oriented towards performing geospatial analytics on Spark. So I first want to demystify why we are using Spark for performing geospatial analytics at scale. Do you have experience working with Apache Spark or? Okay, great, there are a few. So what is Apache Spark? It's a very fast processing engine that is utilized for efficient analysis of vast amount of data. So I heard the definition by, I think, IBM. They call it a dumb engine. It knows how to, it can process vast amount of data at scale, in parallel, blah, 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 but it doesn't know how to do it. So you need to tell Spark what transformation and how this data should be processed. And I believe this really describes Spark well. Why I love Spark? Because it's really performing really good compared to some other solutions. So it's really common tool in many architectures, it's well supported, and the features it provides are really, really rich. Besides this, Apache Spark provides very rich APIs in Scala, Python, and R, so we can write, let's say, convenient code for humans, like code that is humanly readable. We don't have to write Java or C or C++. It provides really rich APIs how to deal with the data, and it is applied across architectures. Of course, I'm not saying that C++ and Java are bad. If you know how to write them fast, that's really good. In many production cases, we need to go back to these languages, but it's really easy if you're working with some, let's say, exploration, you want to learn something new from the data, to have this rich high-level API so we can easily get to new information from the data. Of course, we can use SQL interfaces through data frames, so we can write SQL to retrieve some data, and it has different components that tackle with the performance, so we can optimize all of our code, etc. So those are the main reasons why we were looking for a solution that can perform geospatial analytics on top of Spark. Besides that, we have some machine learning algorithms implemented based on Apache Spark machine learning library. So we wanted to have everything in the same platform, so we don't have to add a new component that needs maintenance or something like that. And what is the situation on using geospatial algorithms on top of Spark? Where there are a few solutions. It's not all of them. I believe there are like probably 3 to 4 more libraries like this. So I just added the most popular ones. First one of them is GeoMesa. It is actually a completely new platform that just provides an interface to Spark. So you can write Spark code to do some, let's say, spatial processing on top of Spark. It is actually a suite of tools for persisting, querying, and analyzing spatial data at scale. It has really rich APIs. So for many things that you want to write in terms of geospatial analytics, it's already there on the GeoMesa, but it is completely new platform. So once you install GeoMesa, you want to use it, you have one more system to maintain and run in production, etc. There is GeoSpark, which actually extends the Apache Spark with a set out-of-the-box RDDs, how they call it, spatial resilient distributed data sets, that perform some sort of spatial analytics efficiently, but they have really missing features. So a lot of features is missing from the API, and it's not that well supported. So no many community people involved to support the tool. There is this spatial Spark, which performs two things really well. So it can support very efficient spatial joins, but various other operations are missing. And the fourth one is Apache, is the Magellan. That's one new library that we are currently using. So I will talk more about the Magellan. And it's slightly old project. It's not that new. And it was developing quite fast for quite some time, but recently I cannot see that people are really involved also in this, for this library. So I believe there might be there's maybe a chance to write something new in terms of geoanalytics on top of Spark. Why we decided to use Magellan for our projects? Well, one of the main reasons is that Magellan is really simple and really easy to implement a new application that will be using it. So what is Apache? What is the Magellan? It is a distributed execution engine for geospatial analytics that is implemented on top of Apache Spark to scale out the computation. Why is this important? Well, let's say that we want to write a new application that will do some geospatial preprocessing or analysis. We would use Magellan as a simple library. So as you would commonly use, let's say, a library to connect to Elasticsearch, you will just add a new package that will support Magellan. And in general, it leverages the modern database techniques like efficient data layout, code generation, query optimization. So it basically becomes like a completely new engine to support geospatial queries. In general, it is set out to bring the simplicity and intuitiveness, so we can write simple code to be scalable and to be flexible and extensible. Why is this important? Well, first of all, in terms of simplicity and intuitiveness, so we don't waste, actually not waste, but so we don't spend too much money for our data scientists to write complex geospatial queries. So they have a simple API to do some fast prototyping or write fast applications. So they can get to some information, then waste days or months to write something really complex in terms of coding. Scalability, so that we as a coders don't have to dedicate our time to scaling our algorithms. So we can have like a platform that will scale by itself, by default. So we have like an engine that does the scalability, so we don't have to deal with it. Okay, in many cases we do have to deal a little bit with the scalability, but with Spark we are trying to actually use the Spark for all of these scalable things, so you can, the engine itself can do this part for us. In terms of flexibility and extensibility, so we don't have any features, some features supported, so we can easily write it or add something new to the equation, so we can do calculation. And it also provides catalyst optimization for data frames, so we can write applications in our favorite languages like R, Python or Scala, whatever we do. Actually, these things are not quite there yet. So if you're using Magellan, you will probably use Scala, but that's okay, we don't have to go to Java. It provides simple APIs, so we're writing less code. It provides high performance algorithms and query optimization, which is handled by the Spark. So it is handled by the core engine itself. So we don't have a new engine to maintain within our company for our projects. You can see here, you will have the slides later, there is the link to the project. In terms of the geospatial types that Magellan supports, we have points, lines, polylines, and polygons. And here you can see how I created some sequence, let's say, of elements, -1, -1, -1, 1, 1, -1, transfer that to x and y, so latitude, longitude, x-axis, y-axis. And then represent that as a point. So I have a new point type for some application. In terms of support to geospatial formats, it's not that rich. It supports shape files, so including metadata. So if you have some data represented into shape files, it can be easily, actually by default, read into Spark application. It provides GeoJSON, and this is the next thing that we're waiting for probably 2 years to be implemented. They're probably going to take some more time to implement this. In terms of the operations, it provides really basic expressions like contains, intersects, within, so whether a certain point is whether the point is contained by a polygon, or whether two lines intersect or something like that. And also binary expression like intersection. So give me the result of intersections of these two polygons. So what is their intersection, like a join. And it provides joins and indexing. Of course, do you know what is broadcast Cartesian join? Is somebody familiar with this term? Okay, this is one of the cool features of Magellan, one of the reasons why we are using it for our projects. So whenever we have two tables where one is really small and the other is really, really huge, since in Spark we don't have the primary indexes, this smaller table will be transferred, actually sent to each node within our cluster. So we'll have the representation of this smaller table, and then all this big data will be shuffled through the network, but the joins will run faster on each of the nodes because we don't have to transfer these smaller tables between nodes. And Perform supports different sorts of indexing, etc. In terms of simplicity, working with Magellan types feels like working with a native Spark code. So here we are filtering a certain point. So we have a point represented with these two coordinates. And we are filtering all the points that are contained within polygon. And this is just some column that we call polygon. So we have a polygon, let's say, presenting our city. We want to display all the points of certain events that occurred within this city. In general, how does it work? So it uses this Answer Java API. I already mentioned that Java has really good implementations of algorithms that perform geospatial analytics. So by implementing Magellan, they try to do the same. So use all the flexibility and already implemented code on top of Java, so we can avoid the serialization. So once that we write, let's say we read in some shapefile and we write some operations, it won't be transferred to Scala, data frames, etc. But all the work that can be done will be done by the native Java API. And when we write these declarative commands, the Catalyst engine, which is a part of the Spark, will deal with the optimization. One of such optimizations is this broadcast Cartesian join. So we have one of the tables that is really small. It will be sent to each of the nodes within our cluster, and that's how we will perform our join operation. And else, if we cannot avoid, we will do just the Cartesian join, where all the data will be shuffled to the network. Also, this z-order curve indexing to speed up our queries. So when we write some query, we have indexes implemented and we don't have to rebuild them by using some algorithms or writing some applications. And when we write some application that contains geospatial query, all this query that was built by Spark when we are writing all of our queries, etc., will be overridden by using these geospatial optimizations that we use in general. What is missing from Magellan? These are the slides from the conference I had last year, so like 10 months ago I gave a similar talk, and all of these features are still missing for Magellan. That is one of the reasons why we maybe will switch to some new solution or actually try to expand something new. For example, one of the things that was not implemented in top of Magellan is that converting from, let's say, UTM coordinates to latitude and longitude was not there, so we implemented it by our own. It's really simple to do some sorts of things like that. For some other more complex things, of course, we need to go back to these algorithms, how they are working. But in general, still the full Python support is missing. Some distance operations and neighbor calculations are still missing from the tool itself. Coordinate conversions, support for some other data formats. But for the use cases that we are using it's really performing really well, and it really allows us to write simple queries to do some kind of operations. And I have a short demo just to show you how does it look like in practice to work with Magellan. Okay, first I will copy, of course I have prepared all the commands here. I will start a new Spark shell with this package Harsha 2010. These are the main coordinates of the project. Let me just see if I can zoom in. Okay. And I will show you the data set that I'm going to use. I have this data set of municipalities where you can see my shapefile. So I have these municipalities in Serbia represented as a shapefile. So if I open this with any editor, I cannot see what is there in terms of the information. But if I go to my Spark application, I will import, of course, the required libraries. And then I will load my data in the format Magellan. Okay, I will need to, yeah, you can see here. So I set here new variable municipalities is spark.read.format Magellan and load the data from this path here. And if I do municipalities.show, okay, I can see here that I have certain polygons and I have some municipalities named in, I don't know what this NG means, probably English. Okay, but this is not humanly readable, so I want to, you can see like this. So you can see municipalities name, Ada, Ojaci, Bogatić, those are all the municipalities in Serbia. And this is the metadata from my shapefile here. There's one column, and another column is the polygon, which contains actually all the dots explaining which area covers a certain municipality. On the other side, I have a TSV file, a tab-separated file, which describes a certain traffic accidents that happened in Belgrade. So it's separated by tabs. So what I will do here with this code, I will split every line by using a tab. And I say, okay, the first column is the ID, the second is the accident date time, then I have location. So as a third and fourth column, transfer to double, etc. So let me see, what does my data look like? Okay, you can see here. So this is the ID, this is the date time where this certain accident happened, this is the point where it happened, this here is whether some damage has been made, and I know what are these two columns here. Yeah, so the type of the accident, a description that was added by the police officers. This is one of the open data sets from our public authorities. So what I want to do now, I want to see all the accidents that occurred by municipality. So I want to see how many accidents, let's say, occurred in the municipality where I live in. Okay. Let me just run my query. Okay, you can see it here. I will rewrite it again. So I said, okay, new variable join data is accidents. So all the accidents that happened joined with municipalities where a location of the accident is inside the polygon describing the municipality. If you have written Scala code, you can see that this is really not that complex. It's quite simple to do these calculations. Okay. Then I want to see, let's say, much cleaner way. It's a similar query. Yeah, so now I see what is the result of this join. So this certain event with this ID that happened on this date, at this point, had this kind of damage description, and I can see that it belongs to Zvezdara, which is the municipality in Belgrade. And last query for today. Let's see what are the municipalities that have most accidents happening, that happened during these 3 years that we have data for. So I have some data set. Okay, let me just go back. So I want to group by municipality name and count the number of accidents, and then I want to order by this number of accidents in descending order. So let's see which are the municipalities that have the worst date. Bad news for me, I live at Beograd, Novi Beograd, which has a large number of accidents, but since I'm not a driver, I don't have anything to do with these results here. Okay, and if we start writing simple queries like this, we can easily do some work, do some exploration. So this is one of the main reasons why we are using Magellan for our projects. And I believe this is it from me for now, and thank you. And I will now switch to questions. Okay. Where do you store geodata that is further processed queried by Magellan? Is it Hadoop, HDFS? Yes, so the largest project we are working with the geodata is for the telco operator, where we are actually trying to identify in which areas certain outages are happening. And we have a vast amount of data coming, I believe it's half of the terabyte on a daily basis of all the, let's say, throughputs that happen in the network and different levels, different KPIs that contain this geographical information. What is lucky for us is that most of this information is represented with just latitude and longitude, but we keep it in HDFS for the scalability purpose, so since we have half of the terabyte on daily basis. And then we're using some maps to compare this data, let's say with municipalities and some other information that we have in terms of geospatial context. Yes?
Should I speak without microphone?
I'm not sure. Do we need a microphone for the questions?
No, I think.
No, yeah, I think.
Thank you for the presentation. You have a slide where you list down formats like the shapefile, all this stuff, the raw context, etc. Do you use any criteria for visual spacing to classify those formats are common, other formats are not? For instance, I have worked with both three, OSM, Eurobase, and raw context, but I haven't ever seen the shapefile. So, from my point of view, I think other formats they're popular. So, how do you classify them? Is there any visual statistics about it?
I believe so. For example, shapefile is used by NASA a lot. So shapefile is heavily used also by the companies that have not, let's say, not traditional geolocation data like latitude and longitude. For example, I believe that oil and gas companies are using this shapefile because they have a lot of metadata that is connected to this information. So maybe there are not many companies that are using these formats in terms of number of the companies compared to, let's say, GeoJSON, but we have a lot of the data that is described in this way. Also, all the dictionaries, all the mappings that we are using, in many cases, are written in shapefile. But I don't have the classifier. That's like from my experience. Yeah.
Number of features that are missing in the original project. We will contribute to the project to make some of them available. Because it looks like the project is very useful, but when?
Yes, that's something that I promised for the previous conference, but I still didn't have the time to do. We wrote a few converters from one format to another, and I promised that I will make a pull request for the project. So I'll definitely have to do that. But one of the things about actually most of these libraries, there are 2 or 3 people contributing to the project. Actually, 3 people are contributing probably to Magellan and one person per each other project. That's one of the main issues in terms of doing geospatial analytics on Spark. So that's why it's one of the biggest issues actually that we have faced so far. Not issue actually, it's really a challenge, but to do something, because you have to do it. It's not, it cannot be an issue.
Your big data fusion, are you using data ingestion from space imagery? You mentioned your work in Shell. You know now lots of example how companies like you using space imagery to see relation with like classic example of observation of car parks, goes to supermarket and so on. What tools are you using for such kind of data injections and to put together with other attribute data?
We are actually not using that sort of information for these use cases. For example, to see how many people have walked through this street, we have the data that comes from the telco operator. So basically, telco operators have tools, geotracing tools that can identify how many people passed by certain street. So do you know how that works in telco? For example, if you're a mobile network operator, if I'm standing here, oops, okay, let me just unplug myself. So if I'm standing in this location and my phone is connected to 3 base station, by using simple algorithms, how far I am away from this base station, from the second one and from the third one, I can easily determine what is my exact location now. But if I have like only 2 base stations that I'm connected to, so if I write my distance from these 2 base stations, the precision is slight lower. And if I'm connected to only one, I can basically draw a circle where I'm probably at. So we're using this similar information to this to identify actually how many people have passed by this street. We are using it only for the, let's say, playground purposes. We are not selling it to any of the customers. We are just doing research in this area because it's still unclear how this information can be used, etc. It definitely can be used on an anonymized level, like, okay, 2,000 people cross the streets today.
I know that if you work with areas or Azure, there are services available to work with SPATIAL data, like monthly database with SPATIAL indices for Postgres available. But if I want to handle data on fly, SPATIAL data fly, like with SPATIAL Spark or Geospatial, is there any edge service available out of the box in the clouds?
In the cloud? Nothing I can remember of. Actually, I never heard about such an engine that can support this. There are some companies that I know are making software for telco companies, and they just do like ArcGIS or something like that. So there are a few companies that really make proprietary software solutions that are selling engines that can perform these kind of scenarios. But I never heard about the cloud solution supporting these use cases. It would be nice to have it. Sorry?
But I think that can just deploy it.
Yeah.
It should be deployed.
Yeah. Yeah, maybe you can just deploy Magellan and then try to offer it as a service. It makes sense, why not? Okay, any more questions? That's it? Okay, well, thank you for being here. I hope I didn't get you bored.